Welcome to Lecture 30, in which I want to give you a deeper and more sophisticated understanding of a concept that you're surely familiar with already, and that's the electrical concept of voltage. You probably know that the voltage available at your standard wall outlets is 120 volts. Something like your electric dryer may run on 240 volts. You know to worry about high voltage, so if you see that high voltage sign, you know that you want to stay away from whatever that sign is marking. You work with batteries frequently, and you probably are aware that batteries are specified by their voltages. Here I have a whole sequence of batteries from the highest voltage one I happen to have available going down. The highest one is a 12-volt car battery. Right next to it is a 9-volt battery, the kind you might put in your smoke detector. It's a lot smaller. On the other hand, it's a lot smaller than the next lower down one, which is a 6-volt lantern battery. You might use this in a heavy-duty camping lantern or something like that. And the rest of them, a D-cell, a 1.5-volt D-cell flashlight battery, a C-cell, perhaps used in smaller flashlights and other applications, and AA and AAA batteries that are widely used in a number of devices. So these are all 1.5-volt batteries. At the very bottom, there's a little button battery like you might use in a very small electronic device, like, for example, a TV remote or a calculator or something like that, or even smaller, you might see one in a hearing aid. These are all 1.5-volt batteries. That's a 6-volt battery, that's a 9-volt battery, and there is a 12-volt battery. I can measure their voltages with a voltmeter, this device, which measures many electrical quantities, but particularly voltage. So here's the 6-volt battery. It's actually 6.4 volts. That's close enough. Here's the 12-volt battery. 12.6 volts. Yep. Here's the 9-volt battery. Let me put it up here so we can see it. 9-volt battery. Yep, 9.4 volts. So these batteries are true to what their labels say. Well, that's the concept I want to explore a lot further in this lecture, because the concept that we think of as voltage is really very closely related to, not absolutely identical to, but closely related to a concept called electric potential difference. And that's the much deeper, more profound concept, and that's going to link us back to the earlier ideas of electric forces and electric fields. So let me introduce you to this concept of electric potential difference, and for the purposes of this course, with one exception, the words voltage and potential difference are essentially synonymous. So you can think of them as synonymous, and I'll point out the one case where there's a slight subtle difference. So we're learning about voltage or potential difference. So let me take an electric charge and let me put it in an electric field. So here I have arrows indicating an electric field that's pointing that way, to your right, my left, that way. And so you can see that that field is a uniform electric field. These are the field lines of that electric field. The fact that they are pointing all in the same direction and the fact that they are equally spaced, they aren't changing how close or far apart they are, indicates that this is a uniform electric field. It has the same value and the same direction everywhere. And I want to take this ball and I want to try to move it from here to here. Now that's not easy. And the reason it's not easy is, of course, this ball being positively charged experiences an electric force, Q times the electric field, as we found in the preceding lecture, and that electric force is that way. And so I'm pushing against that electric force, and so I'm having to do work. It's exactly as if I were lifting a ball against Earth's gravitational field. I'm going, quote, uphill against that electric field, and I have to do work. The concept of potential difference and the concept of voltage are related to the amount of work I do in moving electric charge through electric fields. And very key to that concept is we're talking about moving from point A to point B. We go, and do work against the electric field, or maybe we let the electric field do work on us, accelerating the charge. But the whole concept of potential difference and electric field is about that work that gets involved in moving charge around in electric fields. Work and energy, as you saw with the work-energy theorem back in the mechanics lectures, are very closely related concepts. So I'll often use them essentially interchangeably here and say electric potential difference is about the movement of charge around in electric fields and how much energy is involved in that motion. So let's look in a little more detail about what this concept means. First of all, I'm going to define it, and I'm going to say that the electric potential difference between 2 points, I'll label them A and B, and I'm going to write it all out in gory detail at first. I'm going to call the electric potential difference delta. Delta, remember, means difference, change in or difference. Delta V, V is going to be my symbol for potential difference, V for voltage, if you will. And then I'm going to put the subscripts AB because I want to indicate that I'm moving between 2 points A and B. And by definition, the electric potential difference between 2 points A and B is the work per unit charge needed to move charge between those points. That's what potential difference is. It's the work per unit charge needed to move charge between 2 points, or equivalently, it's the energy charge gains moving between 2 points. Okay. Work, we found out in lecture 11, is force times distance, essentially. Gets more sophisticated if the force changes with position, but basically it's force times distance. Electric field, as we found in lecture 29, is the force per unit charge. So what if I want to calculate the work per unit charge? Well, instead of multiplying force times distance, I'll multiply force per unit charge times distance. So potential difference is essentially electric field times distance. And that's because potential difference is work per unit charge, electric field is force per unit charge, force times distance is work, so field times distance is work per charge, and that's my definition of potential difference. So let's look at an example here. Here's a uniform field. Again, it's pointing to the left on the screen. We want to know the potential difference between points A and B. There's an electric field. I've labeled it E with an arrow over it to indicate that it's a vector, and I'm going to use my definition and find out what the potential difference is between those 2 points A and B if they're a distance delta x apart. So delta VAB in this case is simply the electric field, the force per unit charge, times the distance I've moved, delta x. So delta V in that case of a uniform electric field is simply the product of electric field with distance. If the field is non-uniform, things get more complicated because as I move from point A to point B, the field in this case is getting, well, think about it. Is it weaker or stronger? The field lines are getting farther apart as I move toward B, and so the field is weaker, and consequently, that means I have less work as I move a given distance. And I'd have to do some dividing of that distance into little tiny intervals, or else I'd have to apply calculus. We're not going to bother to do that. But we already did something similar for the case of work back in mechanics when we had a force that varied with distance, and we found that the work was the area under the force-distance curve, or force versus position curve, and consequently, in the same situation, the potential difference is going to be the area under the field versus position curve. So here I have a graph that shows the electric field strength as a function of position. It might represent what's going on there at the left, where the field is stronger at the left and weaker as I go toward point B. And if I could find that area either by some kind of graphical means or using calculus, delta VAB, the work per unit charge involved in moving from point A to point B, is in fact that area under that force versus position curve. So that is electric potential difference, work per unit charge. What are its units? Well, the electric potential difference, delta VAB, between 2 points A and B is the work per unit charge needed to move between those points. Work is measured in joules. Charge is measured in coulombs, so the unit of potential difference is the joule per coulomb, energy per charge. That unit defines the volt. So you've heard of volts. You know you've got 6-volt batteries, 120 volts at your wall, high voltage to worry about. What do those things mean? Ultimately, voltage is about the energy imparted to individual charges. Voltage is the work per unit charge in the SI system. It's joules per coulomb. And a joule per coulomb defines a volt. So if I have a battery, here's a picture of a 9-volt battery. What that 9 volts is telling you is that if you move charge from one terminal of the battery to the other, you will either have to do 9 joules of work, or else 9 joules of work will be done on you for every coulomb of charge you move between those terminals. So let's go back and look at our batteries a little bit more. Think about them in this context of this new understanding. Here's the 12-volt car battery. If a coulomb of charge comes out of here, the positive terminal, and flows through a wire, well, actually, negative electrons would go the other way. We'll get to that in a couple of lectures. But if that were to happen, every coulomb of charge that flowed from this terminal to that one has 12 joules of work done on it. With the 6-volt lantern battery, here's the positive terminal. Every coulomb of charge that flows from here to here through an external circuit has 6 joules of work done on it. Half a coulomb would have 3 joules of work done on it. A sixth of a coulomb would have a sixth of a joule of work. That's what that means. Pick up the 1.5 volt battery. What does that mean? It means for every coulomb of charge that goes from the positive terminal to the negative terminal, the battery gives it 1.5 joules of energy. That's what voltage is. It's about energy per unit charge. Voltage is a measure of the energy involved in moving between 2 points, moving electric charge between 2 points, and it is the energy per unit of charge involved in moving between those 2 points. Now, there's a term I've stressed over and over again here, and that's the idea that we're talking about 2 points. Each one of these batteries has 2 terminals, 2 places I can connect things to it. 2 terminals, those springy things on top of there. 2 terminals on the 1.5 volt battery, the top and the bottom. 2 terminals on the 9 volt battery, the 2 snap connectors. 2 points. Voltage is a property of 2 points. People who don't understand voltage miss that, and consequently they misuse the term voltage, and that can have serious, real consequences. I've seen people misunderstand voltage and hook up car batteries when they're trying to jumpstart a car wrong and with disastrous consequences. You have to understand that a volt is a property of 2 points. It's about the work involved in moving between 2 points. The fact that we've now defined the volt gives us an alternative measure of electric field strengths. We were measuring electric fields as newtons per coulomb. I'm not going to go through the math of this, but if you work out the newtons per coulomb in SI units and work that out in terms of volts as joules per coulomb, you will find that you can write newtons per coulomb equally well as volts per meter. So volts per meter of distance is another measure of electric field strength. So let's look at an example where it's really important that voltage is a measure of work per unit charge or energy per unit charge involved in moving between 2 points. So here is happens to be a news photograph. It's not terribly clear a photograph, but it's a fascinating photograph electrically because it shows a paraglider who landed in a power line, a high voltage power line. Danger, high voltage. Well, he's in real danger. He's sitting astraddle the power line, as you can see, and with his hand he's grabbing the power line for stability. How come he hasn't been electrocuted? Well, if you really understand potential difference as the work or energy per unit charge involved in moving between 2 points, you'll understand why he's not being electrocuted. Or if you see a bunch of birds land on a high voltage line, why aren't they being electrocuted? It's not because the wire is insulated. It's not. No sense insulating high voltage power lines. It's because potential difference is a property of 2 points. And unless you're in contact with 2 points that are electrically different, you are not going to get electrocuted. And that's what's happening with this paraglider. He is in a situation where if somebody reached up from the ground and grabbed him, both of them might get electrocuted. That's why you see those signs on cherry picker trucks saying, danger, don't touch this truck, because if the person up in the boom of the truck is accidentally touching a high voltage power line, they may be okay, but once you touch it also and make the contact to the ground, you got a problem. So potential difference is about 2 points. Why is potential difference even useful if it's about 2 points? Do I have to tell you every time what those 2 points are? Well, I sort of have to tell you the 2 points. But here's what I don't have to tell you. I don't have to tell you how I get from one point to the other. And the reason I don't is because the electric force is a conservative force. Now, way back in mechanics, we talked about conservative forces. They're forces that when you do work against them, as in gravity, lifting a ball against the force of gravity, you can get that energy back again. The energy you put in, the work you did, is stored as potential energy in the case of a conservative force. And like gravity, the electric force is also conservative. And we found out with conservative forces that it doesn't matter what path you take to get from point A to point B, the amount of work had to be the same. And I gave you a little proof of that for the mechanical case. And the electric force is also conservative, so it's true for electricity as well. And that means if I talk about point A and B and I say, what's the electric potential difference between them? It doesn't matter whether I take that nice straight path between A and B where it might be reasonably easy to calculate the potential difference, or I take some curved path like that, or I take some complicated looping path like that. It doesn't matter. I guarantee you the answer for the work per unit charge to go from A to B by any of those paths will be the same. On that complicated looping path, I may have work done on me as I'm going backwards toward A briefly, but it will all compensate in the end, and the amount of work it takes to move a unit of charge between point A and point B will be the same. If that weren't the case, then this whole concept wouldn't be very meaningful. And I will show you cases later on with a different kind of electric force, sort of, where, in fact, it isn't conservative. But for now, the electric forces we've encountered due to electric charges are conservative, and so this concept of potential difference is useful because all I have to tell you is, I want to go from here to here. Doesn't matter how I get there, the work involved is path independent. That's potential difference. And let's pause and do just a simple example on our big screen involving potential difference. Very simple example. We can talk about thunderstorms. We're going to talk about the voltage that develops as a result of thunderstorms. Now, it so happens that even in fair weather, there is an electric field in normal fair weather air of about 100 volts per meter. That means between my two hands, a meter apart, there's a voltage of about 100 volts. Now, wait a minute. How come I'm not getting zapped? Well, because I'm such a good conductor compared to air that I've basically short-circuited that out, and by putting my hands there, the electric field has gone away. I've drained the charges off that are giving rise to it ultimately. But under normal fair weather conditions, there is this electric field in the fair weather air. The air will break down, meaning that electrons will be torn off air molecules and the air will become a conductor in fields of about 3 million volts per meter. So we're very far from that in fair weather conditions. On the other hand, under a thunderstorm cloud, there's typically an electric field of about 10,000 volts per meter. And incidentally, that field is pointing downward because, as I mentioned earlier, the Earth carries a slight negative charge. And there we are. And the question now is, what's the voltage between the bottom of that thundercloud and the surface of the Earth? So let's assume the altitude of the cloud bottom is typically about 2 kilometers. This is a really easy calculation. What's the potential difference between the cloud and the ground? Delta V was the electric field multiplied by the distance, in this case delta Y because it's vertical. That's about 10,000 volts per meter multiplied by 2,000 meters. 20 million volts, 20 megavolts. That's a big voltage. But that's the voltage between the bottom of the cloud and the sky. Because that's over 2 kilometers, it's still a lot less than the 3 million volts per 1 meter that it would take to break the air down. But in the vicinity of a thunderstorm, the fields can get much higher. And when they do, the air breaks down. And that's what gives rise to a lightning strike. So there's a very simple example where we've done a calculation of voltage. Well, so far I've talked mostly about uniform fields and potential differences, as in the case of that field under the thunderstorm. What happens when the field is changing with position? Well, I'd like to give you some ideas of how you can think about potential differences in such cases. Let me begin with the point charge. We've seen the point charge electric field. It's this radially outward field. It's falling off as 1 over r squared. I want to ask the question, what's the potential difference if I try to move from point A to point B in this diagram in the potential difference in the electric field of the point charge? Well, I'm not going to do the math, but it's similar to something we looked at in Lecture 13, namely the gravitational potential energy associated with moving around in the inverse square gravitational field. It turns out the same thing. It's an inverse R potential difference. So it's KQ over RB minus KQ over RA. And it turns out to be very convenient to ask the following question. What if I started with a charge that was very, very far away from this point charge? I brought it in from almost infinitely far away. And so what we do is we say, let's always make point A be infinitely far from a point charge. Sounds a little odd, but it makes the math real easy because 1 over infinity is 0. So then we can talk about the potential of a point charge as I go from a point A, a distance RA from that charge, to a point RB, a distance RB from that charge, and now I'm going to let point A get infinitely far away so that RA goes to infinity and 1 over RA goes to 0, and then I have a very simple expression. If I'm taking the 0 of potential effectively at infinity, V as a function of position is simply KQ over R for a point charge. I didn't do the calculus to get that result, but there is a very simple result describing the potential in the field of a point charge. Now, I made a big point about the fact that we always have to talk about potential as a difference. And now I'm saying, oh, the potential in the field of a point charge. What I'm really saying is the potential difference between a point infinitely far away and a point at distance r from a point charge is this quantity KQ over R. So there it is for a point charge, and now we can begin to think about potential differences of more complicated charge distributions by thinking about individual point charges. Before we do that, I want to take a digression into something that seems to have nothing to do with electricity, and that's a digression about maps. So here's a picture of a mountain in our three-dimensional world. Well, when you go hiking in the mountains, you don't carry a three-dimensional holographic map, probably. You carry a flat map, or you've got one on your GPS device or whatever. That flat map represents the third dimension with contour lines. So here's a contour map of that same mountain. And you can see where the contour lines are close together. The map is the mountain is steep. That means the height and consequently the gravitational potential energy are changing rapidly with distance. We can do exactly the same thing for the electric case. We can think of electric fields the same way we think of the strength of gravity as you look down a mountain slope, the gravitational force component down the slope. And we can draw things similar to these maps. Here's an example. Here is on the left a three-dimensional plot of the potential of a dipole. It's in a plane. It's because the dipole exists in three-dimensional space, and I'd have to do a four-dimensional map to show that. So this is a slice in a plane containing the dipole, and you can see that tall mountain-like structure on the right. That's the potential as a function of position associated with the positive point charge. The hole on the left is associated with the negative point charge, and the two of them combine to make the potential of the dipole. You can see in the picture on the right where I've drawn both the electric field of the dipole, that's the yellow structures that are going out in those loops we've already seen for the dipole, but I've also drawn now the dipole equipotentials. Lines like contour lines on a map which give you regions where the potential is the same. You could walk around one of those curves or carry a charge around one of those curves and you wouldn't have to do any work. Just like you could walk along a contour line on the side of a mountain and you wouldn't be going up or down, so you wouldn't be doing any work against gravity. So we can represent equipotentials by these contour line-like things, or represent potentials by these contour-like things we call equipotentials. And you'll notice the equipotentials are at right angles to the field. They have to be, because the only way you can do no work moving against the field is to not move against it, and that is to move at right angles to it. So there's a potential map, the dipole. And let's look at a couple more potential maps. Here's a map. This is an actual data of a human torso. You can kind of see the torso in the background. These are equipotentials taken on the body. And this is essentially what doctors do when they take your electrocardiogram, except they're not mapping out hundreds and hundreds of points. They're maybe taking a dozen points or so and measuring the voltages, and they're telling you something about the heart. And if you map out the equipotentials in this case, down on the right is a region of positive potential, on the left is a region of negative potential, like that hole in the case of the dipole. In fact, this picture is showing you that the heart has a dipole-like structure, and that in the heart there is an electric field that points from the positive region toward the negative region. Now, I should say the heart, of course, is dynamic. It beats, and its electrical structure changes with time, and that's what electrocardiograms show us. But there's an example of how the heart would tell us something about dipole equipotentials, and using equipotentials to understand what's happening in an electrical system. Let's take another look at such a system on our big screen. So here I have a map of some equipotentials, and I'm asking the question, what's the greatest electric field in this region? Well, if this were a contour map, and I said, what's the place where the mountain is steepest, you would go to where the contours are closest, and you say the mountain is most steep there. Same thing here. The electric field is greatest here. Furthermore, I'm going from 40 kilovolts, that's sort of high up in mountain analogy, 30 kilovolts, 2010. That means downward is that way. The electric field is pointing to the left in that region. So there's what the electric field looks like. That's the maximum electric field in this region. By the way, I've labeled these contours with measures of potential. They're all relative to some place where the potential is defined to be zero. So what's the greatest electric field here? Well, we've gone from 5 meters where the potential is 40 kilovolts to 2 meters where the potential is 10 kilovolts. That's 40 kilovolts minus 10 kilovolts. In 5 meters minus 2 meters, that's 30 kilovolts per 3 meters. That's 10 kilovolts per meter. A volt per meter is equivalent to a Newton per Coulomb. So the answer to our question is 10 kilonewtons per Coulomb to the left. What's the force, just incidentally, if we put, say, a 1 millicoulomb charge in that field? Well, the force is always the charge times the electric field strength. That's 1 millicoulomb times 10 kilonewtons per coulomb. That comes out 10 newtons. You might say, how did I get that? Well, in fact, I took the milli, which is 0.001, and it canceled the kilo, which is 1,000. So there we are. So that's the concept of equipotentials, analogous to contour lines on a map. Well, let me end with one other additional consideration involving equipotentials. I'd like to think now about what happens if we have an electrical conductor. Now, one thing about a conductor is a conductor has no electric field within it, and if you think about the electric field right at its surface, if the conductor is in equilibrium, the field must point perpendicular to the surface because charge can't move around on the surface, and if the field had a component parallel to the surface, charge would move, we wouldn't be in equilibrium. And since the equipotentials are at right angles to the field, that means equipotentials right near the surface have to be basically parallel to the surface. So let's look at an example. Here's a charged conductor, some irregularly shaped object, and as I try to draw equipotentials around it, the ones closest in are going to hug that surface, and the ones farther out are going to become less hugging of the surface, and eventually, if I went very far away, because we proved earlier that a charged object, if you're very far from it, looks like a point charge, they'll become circular, like the equipotentials would be around a point charge. And consequently, if we try to draw the field lines, we see that they have to concentrate in the regions where those equipotentials are hugging around that pointed part, and that means the electric field of a charged object is going to be strongest where the object curves most sharply. And I want to do a demonstration of what that means. So let's move over here where we have our Van de Graaff generator set up again, and we have a couple of objects nearby. Right now, I've got the Van de Graaff set up, ready to go. I've got a smaller ball there. The smaller ball is connected by this wire to the ground through the electric power line, and so it is going to draw charge off that charged sphere of the Van de Graaff when it charges up. And let's look at what happens as the Van de Graaff charges up and we feel a very big potential difference between these two spheres. By the way, the field of these spheres, since they're spherical, looks sort of like the field of a point charge, radially outward, and the equipotentials are sort of spheres around those. So here we go, turning it up. And as it charges up, we begin to get some sparks jumping. Not very many. And not super strong. Let's watch them a little bit. Okay, but now let's replace that object with another one. Discharge that. With the pointed one, whose pointed end is going to face the Van de Graaff, about the same distance apart, and I will bring it up again. We draw a spark a lot quicker. We're drawing more sparks. And I think you'll agree that if we look close up, they're more dramatic looking sparks. So why are we interested in this? Is this just some kind of gee whiz demonstration? No, this is really important because it means if you're designing systems that operate at high voltage, you need to avoid sharp corners. Here's an example, a picture showing what's called corona discharge on a power line. It's a place where we have nuts or bolts or something with sharp edges to them on a high voltage power line, and we actually get strong enough electric fields that they break down the air, and we're actually losing electrical energy to these sparks that are jumping off the power line. So avoid sharp corners on power lines unless you happen to be studying lightning or want to draw lightning to a lightning rod. Here's an example where researchers studying lightning have shot a very thin wire up into the air, trailing behind a rocket, and they generate lightning as a result of that. They're doing it under a thunderstorm, and they're able to make the lightning happen when they want it to because they've developed very strong electric fields. The breakdown of air occurs, and the charge from the thunderstorm dumps onto their wire, and they get lightning. So unless you're studying lightning, or maybe you can safely handle the current, which happens in tall buildings with metal frames. They're struck by lightning many, many, many times without any damage because the heavy metal within the building can move that charge right down to ground without any problems. So you avoid sharp corners when you're dealing with high voltages. Well, let me end with a quick summary of Lecture 30. We found that electric potential difference, this key idea very closely related to voltage, is the work per unit charge needed to move charge between those 2 points. Again, voltage is a near synonym for electric potential difference. The unit is the volt. What a volt really means is energy per charge. It's 1 joule per coulomb is the definition of a volt. We can calculate the potential difference as the electric field times the distance, at least in the case of uniform electric fields. The point charge potential falls off like 1 over r. The work per unit charge to move from infinity to a distance r from a point charge. Equipotentials help us describe contours of constant potential. And finally, we get strong fields where conductors are sharp and we can understand that in terms of drawing the equipotentials around those sharp corners.